working the right way, then you would have seen them come together on the strings. And if I were able to get them charged with like charges, then they actually bend apart from each other. All right, but we did see this happen between the plastic tube that had a negative charge and the balloon which had a induced positive charge. And also between the plastic tube and the pieces of paper. All right, so another way to think about this is to think about it like Newton's third law. Every action has an equal and opposite reaction. And so there's actually a repulsive force between any two like charged objects. All right, so there's a force that object A is pushing upon object B that causes object B to move this way, and a force that object B is pushing on object A that pushes object A this way. And so they repel equally. There's also something that happens with neutral objects. So, and this really goes to the heart of the demonstration that I just had with the plastic tube and the paper. The plastic tube, I induced a negative charge on that plastic tube by rubbing it with a wool sweater. And the neutral object in that case was the paper. And so there was an attraction because the paper didn't have any charge, but because it had less negative charge than the negatively charged tube, then there was an attraction between them. So static electricity works between something that is charged and something that is neutral, which is why if, especially in the winter, you rub your feet against a carpet and then you touch something neutral, you can actually see a spark because there is a lot of electrical buildup on you, a lot of negative charges built up on you, and those get discharged immediately to any sort of other neutral object. And if that other object is positively charged, then it will be double, all right? That will be a huge difference between those two, which, by the way, is pretty much how lightning works too. So I breezed through that because really all you need to understand about charges and fields for right now is that there are negative and positive charges. Two negative charges repel, negative and positive attract. That's really what you need to understand. So let's get down to the math of this, which is Coulombs Law. So electrical force we express as a vector. Obviously, vectors have a direction. So if we have two negative charges, then that vector is going to be pointing away from the other charge. We see here, the vector is pointing away from, on object A, the vector is pointing away from object B, and object B, it's pointing away from object A. C and D are oppositely charged. Those vectors are going to be pointed towards each other. Here's the math. Here's Coulomb's law. The electrical force between any two charged objects is directly proportional, meaning opposite side of the equation, but same side of the division symbol. All right. So as this increases, this increases. That's what it means. That's what directly proportional means. It's directly proportional to the product of the quantity of charge on the objects, how much charge there is. We'll see how to count that. And inversely proportional to the square of the separation distance between the two objects, meaning as this distance increases, the force decreases. As these charges, as the quantity of the charges increases, the force increases. But as the distance increases, the force decreases. Let's think about this for a second. If we have a ton of charge, we just rubbed our feet on that carpet, or I just rubbed that tube with the wool for like 5 minutes straight, there's going to be a greater electrical force. Now, if I bring that plastic tube right up to the pieces of paper. That distance is super small, and that will make the force really big. But if I hold the plastic tube all the way across the room, all the way over here, and pieces of paper are all the way over there, that distance is huge, and that force goes way down. Okay, so electrical forces, electrical charges that are really close to each other have more force. Electrical charges that are individually big create more force. Go ahead. I'm having a lot of trouble hearing you. I don't know if it's just me.
Yeah.
It's better.
Okay. Is it because part more
I could not hear you. Can you type it out in the chat? Am I the only one? Someone let me know if I'm crazy or not, please.
No, I can't really hear it either.
Okay. So while Layla types out her question, the quantity of charge on object 1 is Q1, and it's measured in coulombs. He was a dude. Now he has a unit named after him. All right, just like Newton was a dude, has a unit named after him. So capital C is coulombs. Q2, the quantity of charge on object 2, as measured in coulombs. D is the distance between the two objects as measured in meters. No surprise there that it's measured in meters. And then if you were paying close attention, you saw in that formula that there was a K, a lowercase k, and that is a constant. All right, and according to Coulombs law, that constant is equal to 9.0 times 10 to the 9th Newton meter squared over Coulomb squared. These units make everything work. So you're always going to be given K. It's something worthwhile for the purposes of this lecture to write down somewhere to make a note of so that you can continue using it. But the value is the most important thing really, and that's 9 times 10 to the 9th. Right? That's a big value. So what that means is that a Coulomb itself is enormous. You are not really going to be dealing in your personal life with a Coulomb of charge. That would be a lot of force that would end up creating. So really we're going to work with microcoulombs and nanocoulombs. And in fact, throughout this simulation, we'll be dealing with nanocoulombs, which is like a billionth of a coulomb. All right. So Layla's question for those of you who are in the chat, does the distance make the force smaller because the further you move with the electricity, the more energy you lose along the way? Or is it because the objects are far apart, so the force is just smaller? It's really more of the second. Just like with gravity, the further the distance between those two objects, the less the gravitational force between those two objects. And so electromagnetic fields work in a very similar way to gravitational fields. The further those two charges are away from each other, the less force that exists between them. And hopefully the simulation will help to clear that up, what it looks like along that gradient. So let's practice a little bit with Coulomb's law. And I'm going to go ahead and make sure that you are looking at Coulomb's law, and so that we're not just talking about it. So let's write this out. F equals K times Q1 times Q2 divided by the square of the distance. Okay? And remember that K equals 9 times 10 to the 9th Newton meter squared Coulomb squared. That's a hot mess. Not having superscripts is killing me. But that is the formula, and here's the value of K. So let's walk through this first one together. Suppose that 2-point charges, each with a charge of 1 Coulomb, and that's with 3 significant figures, are separated by a distance of 1 meter. Determine the magnitude of the electrical force of repulsion between them. So again, these are enormous charges. Like, this is lightning storm kind of charges here. And this is meant to be a pretty straightforward problem. So F equals, let's just keep that K in there for now, make our lives easier. What is the charge? What is Q1?
1.
Yes, and for this, and when we deal with charges, let's make sure that we're always saying positive and negative, because those obviously play an enormous role in electricity. And what's Q2?
1.
Yep, but we need to say not just 1, but
Positive 1.
beautiful. And then what is the distance between the two?
1 meter.
Right, so we can simplify that. Oh, I'm doing this in white. It's about to be bad. All right, we can simplify that. We've got 1 times 1 divided by 1 squared. And so we see that this is going to be equal to K, because that's all just multiplied by 1. And we know that K is 9 times 10 to the 9th. And this up here is, oh, somebody didn't tell me about units. 1 Coulomb, 1 Coulomb, 1 meter squared. And those coulombs cancel out. Coulomb squared, meter squared, meter squared. We end up with newtons. So that's 9 times 10 to the 9th newtons. That's a lot of newtons. That's a lot of force. That's why I'm saying that these, that 1 Coulomb is a whole huge amount. All right. So that's generally how we're solving these problems. I'm going to keep the formula up in the upper left. I'm going to get rid of this guy here. And
So
we'll
go
ahead.
You wanted to simplify that?
So Layla, an impression of what I heard was, do you want us to simplify that?
Okay.
So what I heard was something about simplifying that. I always want you to cancel out units. I don't know if that answers your question. So 2 balloons are charged with an identical quantity and type of charge, negative 6.25 nanocoulombs. They're held apart at a separation distance of 61.7 centimeters. Determine the magnitude of the electrical force of repulsion between them. All right, so a nanocoulomb, and I'll put that up here. 1 nanocoulomb equals 1 times 10 to the negative 9th coulombs. I want you to give this a try, see what you come up with. So you may find it helpful, in order to keep track of your units, you may find it helpful to convert units at this step. I'm just going to leave that as K. I want to avoid confusion here. So when I convert units, I get this mess. And I'm hoping that you know how to do multiplication and division with all of that scientific notation in there with exponents. I'll give you a minute to work on that. So negative 6.25 times negative 6.25. Let's do that part first. Let's get those two. So what does that equal? Does nobody have negative 6.25 times negative 6.25? Awesome. What is that with significant figures? So there's 3 significant figures, so that rounds off to 39.1. And then let's multiply the exponents together. So we get 39.1 times 10 to the negative ninth times 10 to the negative ninth equals 10 to the 18th. Negative 18th, good. Huge difference between those. One is an explosion and one is a... And we're multiplying coulombs times coulombs, so we get coulombs squared. Right? That's not scientific notation because this obviously should be between 1 and 10, but we're going to leave that for now. It's the interest of solving the problem. So then we have 0.617 meters squared. So what do we have for the denominator? 0.617 meters squared. What does that equal? Beautiful. 0.381 meters squared. So let's just simplify those numbers down. Okay. So let's treat the exponent differently. Let's keep the exponents separate, and let's just take that 39.1 and divide it by 0.381. I get 102 times 10 to the negative 18th coulombs squared over meters squared. And of course, we can't forget that K in there. And then this last step should clean everything up for us, as we need to spell out what K is. Nine times 10 to the ninth Newton meter squared divided by Coulomb squared times all this mess, 102 times 10 to the negative 18th Coulomb squared over meter squared. Well, now we can at least get rid of some units. We can cross out the Coulomb squared meter squared and the meter squared Coulomb squared. I'm just going to do that for the sake of my little whiteboard here. So now we're just left with newtons, and we've got 9 times 102, which is 918, and we've got 10 to the ninth times 10 to the negative 18th. So what does that get us? 10 to the ninth times 10 to the negative 18th. That's 10 to the negative ninth, beautiful, coulombs. And we need to get that into scientific notation, which means that we need to move the decimal point over 2 places so that it's 9.18, because that first number needs to be between 1 and 10. And since we're taking away 2 decimal places, that means we're dividing by 100. All right, we're dividing by 10 to the negative second, 10 to the second power. Okay. So we end up with 9.18 times 10 to the good, negative 7th. I'm sorry, I put coulombs. That's newtons. We know that's newtons. So that ends up being a very small force. Okay, we know forces. We know what a newton feels like. That is less than a millionth of a newton. It's a very small force, but it doesn't take very much force for in the electromagnetic world to make things happen. Okay, so I know this is a lot, but there's a couple tricks in here. One of those is being able to work with exponents. Another one is that when you get this k in there, this constant k, that it cancels out your units for you. It gets you back to newtons. So all that mess of units should cancel out. If it doesn't, then you did something incorrect in the math. But make sure that you are getting to coulombs and meters. So for the purposes of today, I'm going to leave the last example for tomorrow. I want you to play around with the simulation today. So I am heading to the simulation real quick. You can watch what I'm doing and then do it yourself. So in order to use this simulation, I can take positive, negative, and positive charges, negative charges, and sensors. All right, I'm going to start with the electrical field. I just want to have the electric field. I'll take a positive charge, and it's showing me the electric field. It's showing me that the field is emanating out from this positive charge in all directions, and that it's stronger right here, and it's weaker out here. I could take one of these sensors, and if I drag the sensor into the field, it'll give me a vector quantity of how strong that charge is and also what direction it's pointing in. So as I drag this around, this lets me see how strong or weak that relative field is, that electrical field is that is created by this charge. Okay, that's what we're measuring with Coulomb's laws. We're measuring the force in any particular place. And we notice that as we go further away from that charge, then that force really goes down quite a bit. And the closer we get to the charge, the higher it goes. Now, what you're going to do is you're going to be playing around with all sorts of combinations of different charges. All right, these are measured in nanocoulombs. So if we put a different charge in here, we see how the field completely reorients, right? And there's all sorts of different vectors that pop out as a result. One note about this simulation is that to get rid of a charge, you simply drag it back down to this box and release. And that's how you can get rid of the charge. You are going to want to have the grid on because I'm going to ask you to do things aligned to the grid. Pay attention to the major grid markings. I refer to the major grid markings in the activity. The minor grid markings are less important. Just make sure you're on those major grid points like I'm traveling between right now. Questions?